Hi, this is Wenqian, and here I will give a brief introduction on my ICCAD submission at AdaOPC, a self-adaptive mask optimization framework for real design patterns. This work is in collaboration with Xufeng, Ziyang, Guojin, Chen, and Beiyu, and Martin D.F. Wong from the Chinese University of Hong Kong, and Yuzhe from Hong Kong University of Science and Technology, Guangzhou. So before I talk about my main work, I want to give some brief on the background and motivations. So as the feature size has been shrinking towards the extremely small scale, in the advanced technology nodes, there are some resolution enhancement technology need to be applied to tackle the crucial optical diffraction and approximation effects, while OPC, short for optical approximation correction technology, is one of the most famous one. And so there are some existing OPC methods. First one, there are some heuristic rule-based OPC methodologies, as you can see here. And also there are some model-based OPC methodology to model the distance between these edges and slice them into different cuts and move them accordingly. And also there are this LRT-based methodology, which is short for inverse lithography technology. Basically, it doing the forward simulation of the lithography, and it compared the output with the original design pattern, calculate the difference as a loss, and calculate the gradient backwards on the backwards the gradient to optimize the mask. And after rounds and rounds of iterations of such updating, the optimized mask will be providing a final output Z with minimized difference with the original design pattern. Okay, and also there are some machine learning based methods to tackle this problem. Well, here, as you can see, the generator is a machine learning model, and given a design, it will be directly output some mask. It can either be used as a final result, or used as an initial mask to the LT engine to save the numbers of iterations. Okay, so all these methods actually have some certain drawbacks. So rule-based methods, it actually does not show enough local fidelity. Okay, and also both rule-based methods and model-based methods, they're actually restricted by the solution space in nowadays advanced technology nodes. Okay, and the LT-based methods actually, it's although it may be really effective with it, but it iteratively calling such calling of the imaging system or the lithography process during the optimization is actually really time consuming. For the machine learning based methods, although it have shown remarkable speed up in the OPC flaws, it's not actually, it's a black box and it's data driven, so it's not guaranteed to work for some critical patterns or the long tier patterns. Okay, and for the lithography, I also want to say this is one of the most famous Hopkins diffraction model to simulate the lithography process, which can be described as a number of convolutional kernels consecutively. And this is the kernel, this is the mask, this is the weight of each kernel, and after that we'll output this intensity thing for each pixel. And after that, it will be then sent to a photoresist model with a threshold to determine whether each pixel is printed or not. Okay, and also these are the EP and the PV band. These two are the most famous criteria to evaluate the quality of the printed pattern. Okay, so they're listed here. Sorry. So after that, now let's come to the motivations of our work. As I said, that all these previous methods, actually, they try to tackle this OPC precise by looking at a small patch. However, in reality, what we're facing is actually a really large full-scale design. Okay, so if we zoom out and look at it as a whole, we can find some interesting discovery. The first one is that all these patterns are actually, they are scattered unevenly with different complexity. So that means we cannot just just without a second thought, just manually slice them into patches and send them to the OPC solvers. We have to treat them differently, probably with different selections. And also the second finding is that, you know, they have a large ratio of repetition on a full layout. So, you know, many of them are repetitive. So we can think about reusing some of the masks. Okay. So that lead to our adaptive framework, which is looking like this. And there are three major parts of our work, which are colored orange. The first one is the solver selection. The second one is the pattern embedding, and also for the shape calibration and the pattern library. Okay, so the main contribution is that we, as I said, firstly, there's a adaptive solver selection, and also there are mask reuse for the critical patterns, and there's a dynamic pattern library which is used to store the already optimized patterns, so that every time when there are so let me talk about it this way. Firstly, when there's a large design coming, we'll slice them into small patterns, right? Like the other methods. And the first thing we do is actually we solve. You know, we classify them into critical and non-critical ones. For the non-critical ones, we want to use some solvers that is maybe not that robust, but it's effective enough for simple patterns, while also shows great advantage in speed. Okay, and for the critical ones, so we choose a machine learning based solvers. For the critical ones, actually, we want to use some rigorous, may not necessarily be fast enough, but rigorous, robust models to solve for them. And for these patterns, actually, you know, as I said, it might, for example, like RT, it's really slow, right? So we want to reuse those masks with the already optimized mask stored in the library. Okay, so if it's a match, there's a match. Okay, so we'll just, you know, do the shift calibration and send them to the rigorous solver for further iterations, which won't take that much time. And if it's a new one, so we will just directly send them to the solver and save them back to the library after the optimization. So this is a whole flow. I will talk about each point with a bit more details. So for example, so the first thing is the model, the solver selection. Well, it's actually really intuitive to use a machine learning model or deep learning model for the solver selection. And basically, this is just simple classification problem. And actually, it's a binary classification. So you just train it with you take patch as an image and you classify them into different. You know, there are two classes, so you can simply use the cross entropy laws to do the classification. And if there are like more than two categories of solvers, for example, if you want to add one, so it's definitely extensible. It's just you need to adjust the loss by adding the number of class like this. Okay, and also for the mask reuse, as I said, like you know, the first thing we do is that we manually slice them into patches. However, even for the same patterns, there will be some pattern shift here. So there's some question here. The first thing is that whether and how can we optimize the mask with local shift be reused? Okay. The second question is, even if the answer is yes, how to match the same pattern accurately within an acceptable time? Because the whole idea is about speeding up. Okay, the third question is how to measure the geometric similarity of patterns with local shift. Okay, so the first thing is whether can we use it. Actually, the details won't be listed here, but in the paper we have shown in that there is a shift equivariance of the lithography process, which means, you know, the design pattern and the printed shape won't be affected by the local shift. They will just holding the shape won't be distorted, and also there will be just a parallel local shift. And in that case, we only need to calculate the pattern shift, since printed mask won't be changed at all, but also with the local shift. Okay, so the weather problem is answered, and the next question is how how can we optimize the mask with a local shift to be reused? That means we have to do the shift calibration, which is also listed in the paper. But here we simply, I will briefly talk about it. So basically, we can calculate the pixel-wise difference of these two patterns by using a cross correlation calculation. By calculating the pixel-wise similarity of the two image. And this actually can be realized by calculating the, the conv FFT of this P and rotated P ply. And this can be really fast calculated with many existing tools. And yeah, so that's also answered how. So the next question is how to match the same pattern accurately within acceptable time. Well, to solve this problem, actually we built or maintain a online updated pattern library to store the features, embedded features, and optimize masks of previously encountered critical patterns. And we want to use the result of the saved masks. Here, the features means that we do not store the pattern directly. Instead, actually, we will store them as some high-dimensional features for faster matching. Okay, so that's also mentioned here. As you can see, each mask will be embedded as a high-dimensional vector. Well, within this library, actually, because the library could be really big after the patterns, more and more patterns are getting there. So we actually use a graph-based library, where each node represents a pattern, and each edge is actually a connection, means the distance of these patterns are recorded, and all these edges are actually represents the closest edges, and also there will be shortcuts in this graph, and all this graph matching and the patching. I mean, all this graph searching and matching algorithm are based on this most state-of-art hierarchical navigable small word algorithm. Basically, it's a most effective, accurate graph matching method, which we applied here, and it's really, it's a sparse hierarchical structure, which is really fast and effective for matching patterns. Okay, another thing is that how to measure the geometric similarity of pattern with different local shift. Well, actually depends on the embedding space for the vectors. So what we want is that we want positive samples or the patterns of the same patterns are similar, and the negative samples, which means the shapes from different patterns, we want to be different. So here is actually we actually use the I mean, many metrics can be employed here, but here in practice, we use the Euclidean distance in our practice. Okay, sorry. And another thing is what we want. Another thing we want to talk about is the embedding. Since the objective of the embedding space are listed here, we can simply use the contrastive learning to learn the embedding space, where in the by proposing such a supervised contrastive loss, we can make sure that in this embedding space, all the positive pairs, which means the shapes from, or the patterns from the same, the shapes from the same pattern are actually close, and well, also the patterns of different the patterns of the different patterns are actually distant enough as visualized in this figure. Okay, and so yeah, that's pretty much everything in this presentation. But also let's talk about the results. As you can see, with and without optimized mask as an initial results for the rigor solver, as you can see, the EPE actually is starting from a very low stage, and it's converged at the very early stage, which really verifies the effective of our proposed mask reuse. Okay, and also for the if you look at the time breakdown, as you can see, the shift calibration and the pattern matching won't take that much time, especially when comparing with the pattern matching. So there will be no that much time overhead. Okay, and also if you look at the mask convergence speed, overall mask convergence speed with without pattern matching, you can see our proposed method is really fast. And these are some results of the, the randomly chosen 10 patterns in comparison with the most one of the most state-of-art machine learning based methods and the RT based methods. And if you look at the runtime and also the EP and PB bands, we can see we have our method actually borrows the advantage of the machine learning model and the precision or the accuracy advantage of the RT method to choose the SOTA in both metrics. And that'll be all from my presentation. Thank you, guys.